Well, here we are having a capacitor circuit and we are going to find the potentials at two nodes. Let us say this is a node N1 and this is a node N2. So we have to get the potentials at these two nodes for the given capacitors and cells which are connected in the circuit, and subsequently after we get the potentials at these two nodes, we can obtain the distribution of charge on the capacitors. So the whole process we can consider as nodal analysis, and just like we do the same nodal analysis in electrical circuits, it is quite similar to that. Okay, so now here we have to do this by considering the isolated system, but before that let us also assume that the circuit is in steady state. Steady state means the capacitors have been already fully charged to the whatever extent they can be charged, they are already charged. That means they are not in the transient state of charging, they are already charged. Okay, so I can consider an isolated system. Let us say this is an isolated system 1, isolated system 1, and let us say this is another isolated system 2. Okay, so there is no flow of charge any further between the capacitors, as we have assumed there is a transient, there is a steady state. Okay, so now let us also assume that charge on this capacitor is Q1, on this it is Q2, on this it is Q3, on this it is Q4, and on this it is Q5. So these are the charges on the respective capacitors. So coming to the first node N1, so just like what we say in Kirchhoff's current law in electrical circuits, the sum of currents, the algebraic sum of currents meeting at a junction is 0. What was current there would be charge here. So I would rather say that Q1 plus Q2 plus Q3 would be 0. Okay, before we can do this, we will have to consider the potentials at the bottom points. See, this is a negative of the cell and this is also negative of the cell. So quite obviously we can say this must be 0 volts. And since the potential difference on either sides of this cell must be 5, so if this is 0, this must be a potential of 5 volt. And again by the same logic, if this is 5 volts here and there must be a potential difference between these 2 points as 10 volts, so this must be 15 volt, right? So we got the required potentials now which we have to use in the expression. So now we can start. So now Q1, I would say, see, we have the formula that if there is a capacitor of capacitance C and potentials on either sides are V1 and V2, so that we say potential difference is V1 minus V2. So we say the charge on the capacitor is Q is equal to CV, which is C into V1 minus V2. So going by the same way, we will apply this for each of these charges. So I would say for the first case, Q1, it is a capacitance of 2 micro, but I would write 2 because micro will be there for all the terms and it would get cancelled. So straight away we can ignore micro. I will take only the numerical value of 2. So 2 into the potential difference, I would say here let us assume that the potential is V1 and here let us assume that the potential is V2. So it is 2 into the potential difference on either sides of this capacitor, it is 10 and V1. So 10 minus V1 plus, coming to the second one. Okay, so here this is V1 and here this is V2. So I would say it is capacitance into potential difference again, so which is 4 into V2 minus V1 plus, coming to the third capacitor, again going by the same sense, it is 2 into the potential difference which is 0 minus V1. Okay, so this must be 0 on the right side. So making the cancellation, it must be 2 here So 10 minus V1 plus 2V2 minus 2V1 minus V1 is equal to 0. So it becomes 4V1 on the other side. So 4V1 minus 2V2 must be equal to 10. So alternately I can say 2V1 minus V2 should be equal to 5. Let this be equation 1. Okay. So now we can treat the same way for the second node. So if I say if N2 is the second node and I would like to write a similar expression at N2, I should say it is Q2 plus Q4 plus Q5 must be equal to 0. So now the same way I would say Q2 is the capacitance is 4 into the potential difference, which is V1 minus V2. Okay, and plus coming to Q4. Q4 is the term here, so I would again say it is 4 into 15 minus V2. And lastly Q5, it is here. So capacitance is still again the same 4. It is 5 minus V2. This must be again equal to 0. So as all the terms are 4, we can make a cancellation. So it becomes V1 is the only term on this side. So V1 minus this is V2, V2 and V2. So it becomes 3V2. And it is 15 and 5. It becomes plus 20. So finally I can write 3V2 minus V1 must be equal to 20. So we can simply now solve the two equations. I got 2V1 minus V2 is equal to 5 and 3V2 minus V1 is equal to 20. So now to make the cancellation, let us make a multiplication of 2 for the second equation. So it becomes 2V2 here with the minus sign and 2V1 here with minus sign and 2V1 here with plus sign. So when we add, these two terms cancel, so that after cancellation I get this is 2 into 3, 6V2 minus V2 is equal to addition here 2 into 20, 40, 40 and 5, 45. So I get 5V2 is equal to 45. That means V2 is 9 volts. So I got the potential of the second node, which is N2, 9 volts. And quite obviously I can get V1 from the equation where I have written 3V2 minus V1 is equal to 20. So it becomes 3 into 9 minus V1 is equal to 20. So V1 would be 7 volts. So I got the potential at the first node as 7 volt. I would better mark it here. So this is a potential of V1 is equal to 7 volt and this is a potential of V2 is equal to 9 volt. So now once we get the potentials of the nodes respectively, quite easily we can get the charge distribution again using the formula Q is equal to CV, where V is the potential difference. Coming to the first capacitor, let us say this one. So I had Q1 is equal to C1V, where I mean V is the potential difference on either sides of this capacitor. So for this the C1 value is 2 micro and the potential difference this side it is 10 volts because it is the positive terminal of this battery, and this side I got the value of 7. So the potential difference is 10 minus 7, so it becomes 6 microcoulombs. So I would say this capacitor has a charge stored of 6 microcoulombs. And coming to the second capacitor, so I would say Q2 must be C2 into, let us say, V dash. potential difference on either of these sides. So C2, the value here is 4 micro. So 4 micro into the potential difference. Here it is 7 and here it is 9. So I would say the potential difference is 9 minus 7 and it becomes 8 microcoulombs. Coming to the charge which is stored on Q3, this one. So the potential difference, this side it is 7 and this side it is 0. 7 minus 0. So I would straight away write Q3 is capacitance is 2 micro, C3 into V double dash, let us assume. So it is 2 micro into 7 minus 0. So it becomes 14 microcoulombs. Okay, so I can mark here for this capacitor it is 8 micro, and for this capacitor it is 14 micro we have got. And now coming to the fourth capacitor here, so I would say Q4 is C4 into V triple dash. So now C4 capacitance is 4 micro, so 4 micro into the potential difference. This side it is 15 and this side it is 9, so I would say it is 15 minus 9, that means it is 24 microcoulombs. And lastly, the capacitor which is number 5, it is Q5 is equal to C5 into V 4 dashes. Okay, fine. So now the capacitance is again 4 micro and the potential difference for this side it is 9 and this side it is 5. So it is 9 minus 5. So it is 4 into 4, 16. So 16 microcoulombs. So I can mark it even. This is 16 microcoulombs and this was number 4. I got 24 microcoulombs. Okay. So this way we can get the charge distribution in a capacitor circuit using nodal analysis. Just the only sequence is first you have to get the potentials. So even before that you have to identify the nodes, and once you identify the nodes you have to solve for the potential at the nodes, and once you get the potentials at the nodes we have to get the charge distribution using the format Q is equal to C.